talk this morning is by Jun Li. We'll talk about the invariance of quantum topology on the flops.
Thank you. So today what I'm going to explain is a joint work. It's a joint project with Professor Lin and Wang, both from National Taiwan University. And so we've been thinking about this for many years. And our main interest is to consider sort of a functoriality of Gromov Witten theory under, just basically functoriality of Gromov Witten theory. What can we say about Gromov Witten theory? What kind of property make it functorial? And so I explained this in very briefly in the summer school. The reason of causing Gromov Witten theory being non-functorial, there are many reasons. And so Gromov Witten theory is usually not functorial because of obvious reason that if you define, so given a morphism from y to x, and we say that if you want Gromov Witten theory to have some kind of pullback property, and the pullback property would have to look like this. So given alpha I inside the cohomology of y, and if you want to define Gromov Witten invariance for alpha 1 up to alpha n, let's say primary invariance, g to g beta, and in y. And if you want this to have some kind of property, and then the best you can think of is to have the pullback. I should say this is in x, while beta is of curved class inside y. And so the best you can think of is to have pullback this. And this, you want this to be the same as alpha 1, alpha n, x, g, and f lower star beta. And so, first of all, this will almost never hold. And in fact, because Gromov Witten invariance, basically, if you think about y and x are both smooth projective varieties, and this is a morphism. So basically, this is a blow-up, and with blow-up, this will never hold for all beta. So this will never hold basically because this almost never true, because we know ky, if it's so the virtual dimension in the y side will be minus ky dot beta plus dimension y minus 3, and then 1 minus g plus number of mark point. And on the x side, it will be minus kx dot f lower star beta and plus dimension x minus 3, 1 minus g plus n. And so even at this level, you want, so in order for this to be universally true, what you need to think of is maybe, to make this universally hold, you want dimension y to be same as dimension x, and then also minus ky dot beta to be the same as minus kx dot f lower star beta. Basically, that's what you want. But this will never hold for all beta, because we know that for example, if this is if this is a say étale map finite cover, then this will a certain degree will happen. And if it's not, then if it's blow up birational, then this ky is the same as pullback of kx plus certain times of your exceptional divisor. And therefore, if your beta has non-trivial intersection with exceptional divisor, then this will never hold. So that's why the Gromov Witten theory would never have full functoriality in terms of morphisms. And so to seek for functoriality of Gromov Witten theory, so for example, if we want something like this kind, and then we will have to think a different way. And to think of this differently, so for example, this leads us to, well, basically, what are choices? You can have birational map, birational morphism, or you can have, well, and you can have this étale finite cover. But as I say, étale finite cover, this term will not hold. So you can think about, maybe I want to have birational map. But birational morphism between smooth projective variety is basically blowing up and blowing down. So then this will never hold. And so that's a problem. So to solve this problem, you will have to think of not just one blow up, but a blow up and then blow down. So that leads us naturally to the concept of this. If I blow this up and blow down, so that, so let's call this phi prime. So if this is definition. So x and x prime are k equivalent so, or sometimes, i.e., x prime is a Crepant transformation of x if we have phi pullback of kx the same as phi prime pullback of kx prime. So I want this to be basically the same. So how can I achieve that? As I said, for blow up, I will not be able to do it. I have to blow up, then blow down. So when they pull back, the difference will not be there for when you take the dot with the beta. So that's what we're thinking of. So this will be somehow the necessary condition. So as I said, this k equivalence or Crepant transformation will be sort of a so this is somehow the necessary condition. For functoriality of Gromov Witten theory. And so you can ask, once you have necessary condition, you can ask whether these are sufficient. And so that's sort of our starting point. Questions? So you can ask whether these are sufficient conditions for Gromov Witten theory to be functorial. And so that is and what kind of things we can study for these? Of course, then if you allow x and x prime to be just smooth varieties, and then the basic example will be flops. And if you allow x and x prime to be orbifolds, then you have more examples in your case. But basically what I want is x and x prime to be sort of Crepant to each other. So of course you can allow x and x prime to be orbifolds, but today I'm mainly dealing with a case of the manifold case. So when x and x prime are manifold, so basically what I'm interested in today. So x and x prime, again, are manifold smooth projective variety. And they are connected by a flop. So as I explained, I want these two manifolds to be birational. So basically, x and x prime will be somehow very arbitrary manifold, but in some locus, I'm doing some kind of surgery. So in the neighborhood of this locus, I remove this, and in this same neighborhood, I attach a different thing inside. So it's only a small neighborhood that I do some kind of surgery. And the rest will be the same. And I want to ask whether the Gromov Witten theory will be identical. So and these two are birational. Means for the open part, they are all the same. And it's only a small neighborhood. And in this special case I'm going to study here is where this neighborhood will locally look like this. So this part we'll call exception locus. And I'll tell you what the locally what they should look like. Locally around. It will look like this. It will be so this part, which I'll call it Z, and I'll call this Z prime. So the Z will look like a projective bundle over. So S is an arbitrary, again, smooth projective. So S is a manifold, and F is a rank R plus 1 bundle over S. So locally, my exceptional locus will be some kind of projective bundle. But as you know, the surgery do concern the neighborhood of this Z. So I will have to tell you what the normal bundle of Z inside this, let's call it X, and X prime. And inside X will be like this. Will be O minus 1 tensor with F prime, where F prime is another rank R plus 1 vector bundle over S. So basically, it's a pullback. So I need to pull this back to Z. So I have two. So basically, so you can see that the data here, local data. Local data is the following: you have a manifold. You have two rank R vector, rank R plus 1 vector bundle over S. And from here, I build this local neighborhood. So let's just say again, local neighborhood look like a projective bundle over an arbitrary manifold, and with normal bundle, which is going to be O minus 1. So what this says here is basically on each fiber projective space, it looks like O minus 1 to R plus 1. So fiber-wise, so for those who know a little bit, fiber-wise, over a point S in S, it will look like O minus 1 to R plus 1 over projective space. So it's like Calabi-Yau. But base is completely arbitrary. So you have fiber look like Calabi-Yau, but base is completely arbitrary. And in this case, one can ask whether this sort of Crepant transformation of functoriality of Gromov Witten theory also holds. So that's the situation we're led to. Questions so far? The setup. In fact, I want to say a little bit more about this because usually there are many versions, as you heard from Renzo's talk. There are many versions of this Crepant transformation, Crepant resolution conjecture. Here I'm referring to the strongest version, namely it will be a predictive case. Namely, I want to start with the following. So this predict. Well, my spelling might be wrong. Model of this Crepant transformation conjecture which means I want to start with the first step. I want to start with the geometry of x and s prime. And then I will build equivalence of their I want to start with geometry of x and s prime, then I'll build the equivalence of their cohomology groups as groups or vector space. Then I will use this f to go to identify the Gromov Witten theory of x and Gromov Witten theory of x prime. So that's a goal. So I want to do a complete predictable system that I will first just study complete local geometry. So classical geometry, maybe not local. I'll consider just classical geometry of x and s prime, and I will form this f which identify their cohomology groups. Then I will use this identification, and I will completely identify Gromov Witten theory of x and x prime. So that's, I think, the strongest version you can get from this Crepant transformation. Is I want to first, so everything about quantum is complete so if you know one side, you completely know the other, just by the classical geometry. That's so the case I'm interested in. As you know from the study by CCIT, or I is here, Yuan-Pin, that if this x or x prime are not hard Lefschetz, then this shouldn't be expected. But so in that case, as I explained in summer school, that you would have to put some kind of hard Lefschetz condition in, and the natural hard Lefschetz condition you can put in is what I call hard Lefschetz K equivalence. Namely, since these two are birational, and so in the outside exceptional locus, even if it's not hard Lefschetz, you don't really care. I mean, they're identified with each other in a way. And in the neighborhood of exceptional locus, you want these two, two neighborhoods, to satisfy the hard Lefschetz condition. So it's sort of a very local hard Lefschetz condition you have to impose on x and x prime. You don't need a global hard Lefschetz condition, and you only need a global hard Lefschetz condition if you're studying Crepant resolution case. Namely, if one side x prime is manifold and x is orbifold, then you certainly, because one side already satisfied hard Lefschetz condition everywhere, so then the other side had to satisfy hard Lefschetz condition everywhere as well. And hard Lefschetz condition can be written locally because, I mean, I'm just making some kind of running comments. For those who know orbifold theory, that you can write that as some kind of the age invariance of age under this G go to G inverse involution. So it's completely local condition. You can write this down locally, and you can test them locally. So that's okay. So, but for today, because I'm not going to talk about orbifold theory, which we're still working on, so I'm just going to talk about the manifold case. So manifold case, that's things I want to explain how to get there. Questions? Okay, so suppose you have this. So suppose that's the goal you set for yourself. The first thing you want to ask is how to do the first step. And as Hiroshi explained, this is sort of a circle idea that's already there, that it has to go through the first identifying x and s prime, the child or k or whatsoever cohomology theory has to come from some kind of Fourier-Mukai transformation. This is the idea. It should be very clear that to identify these two, you want to identify either in K theory or in cohomology theory, child theory, or motifs. It has to come from some kind of Fourier-Mukai correspondence. So to find f. So basically, in this case, it can be very easily described as a correspondence. Well, these two are birational. So let me call it f. And then, so then you have in the finite part, in the open part, you have this graph of these two because they're identified. And so you can take some kind of closure of this. And in this case, I'm just taking the minimal closure, that means scheme theoretic closure of this graph closure inside this. And this guy, and I will define my f of alpha. Alpha is here just by taking the pi 1, pi 2. I will take a pi 1, pull back alpha, then intersect with gamma f bar, graph closure, and take pi 2 lower star. So that's the model I'm going to use. So, and one has to prove that. So the theorem here is that this f identifies so cohomology and in fact also identify Poincare pairing. So this f identify cohomology groups and Poincare pairing. So in fact, it actually does more. It sort of identifies the universal Chow theory, Chow motives. But I will not say what this is. So for those of you know, and then you know how to prove this, and just basically you need to do this by Manin's identity principle, and so yeah. Anyway, so you can identify these naturally by this kind of Fourier-Mukai kind of transformation. It's again in the orbifold case, some kind of comment. In the orbifold case, it would be a lot easier if you do a K-theory, because K-theory orbifold is a lot easier than K-theory of like chain-around cohomology of things. But it will automatically, by some kind of Riemann-Roch map, this Mukai vector will take you from K-theory to that. As Hiroshi explained, also it tells you a lot about the integral structures from K-theory. But anyway, so for our case, this is very good. It identified this. But this f does not identify, it does not take the Moricon to Moricon. You take one side, the cone or effective curve, it doesn't map to, in fact, in this case, it exactly fails when it's in the exceptional locus. So, so in the exceptional locus, so you remember our exceptional locus look like projective bundle over an arbitrary base, and for every fiber is a projective space. So there is exactly this L, which is a fiber curve. And you can find out this fiber curve has been mapped to, on the other side, you have the same fiber curve. It basically looks like the same, the Z prime. In fact, I forgot to explain. So when you do this transformation and flop to the other side, it's exactly like this, F prime. And the normal bundle here is exactly exchange these. So it will be O minus 1 cancel with pullback of F prime. While here, the normal bundle will be exactly like O minus 1 in this side, cancel with pullback of F. So they are all fiberwise Calabi L. And so in the exceptional locus, they're exactly this L. And here you have fiberwise L prime. And this L is mapped exactly to negative L prime. So you see that the Gromov Witten theory cannot, so you cannot get this. There's no way this is going to be true. On X side, with L, this is never going to be true because that won't hold. Which is going to be negative L prime, and therefore it's not effective, and therefore this will be always 0. But this side certainly won't be always 0. So that just make it a no-go. However, as many people, starting with Yuan-Pin's early observation of this Crepant resolution conjecture and everything, so that's why you need this analytic continuation mentioned in Hiroshi's talk, that this will not hold. However, so you need analytic continuation. But if I give this, what I'm going to do analytic continuation with? Well, it's the complexified Kerr parameter, and in the language, in mathematical language, will be the nomical variable with respect to sort of complexified Kerr parameter. And since in our case, there's a specific curve class we're talking about. So basically, we're taking the nomical variable corresponding to L and L prime. So yeah, so that's we're doing analytic continuation with respect to these variables, and therefore to do that, I need to do this. I cannot just find this. I have to sum this over. So I have to sum this Q dl degree and degree. And if I do that, d prime, and I sum over Q d prime L prime. Of course, this goes to negative L prime, so it doesn't really make sense. But what I mean by this is that if you do this, L prime, and these two will be, well, in Hiroshi's notation, those will be this equivalence relation. Namely, this will be, so it will be the same after analytic continuation. So what it says here is the following. So maybe I'll say this left-hand side is an analytic function with respect to certain Q variable, QL, and you can write this, and the right-hand side also is an analytic function with respect to another variable that's called Q prime, L prime. And so they are both analytic functions, and you can say that they are analytic. So left-hand side is equal right-hand side after analytic continuation. So that's the best you can do. And so, I mean, I'm sure many of you heard this like 1,000 times already, but I'm just going to say this in 1 minute. So, for example, if left-hand side is something like summation QD, right? And so, say D from 0 to infinity, and you can write this as a rational function, geometric series. And then what you do here is to rewrite this in terms of Q equal to 1 over Q prime. And so what you end up with is Q prime and then Q prime minus 1. So then you have minus summation q prime to a d prime, and d prime start with 1 to infinity. So that in that case, these two are certainly not equal, but they can be identified after analytic continuation. And so there's this first thing you observe. These two, well, certainly not equal, but they're not equal as a formal series, but they're equal as a rational function or analytic function. The first thing. And secondly, you observe that here you have a constant. You start with constant. Here you don't have constant. So this side has constant. This side doesn't have constant. So that's a very good example in terms of what's going on with this. So now, if I want to predict what's going to happen with this, so I will have to say the following. So what can I say about this? Well, what I want to say about I can say about this is, first, it's a missing constant term. So if I'm summing this as a Gromov Witten generating function of Gromov theory, the constant will not be the same. But you remember the constants are sort of a classical invariance, right? So degree 0 invariance will be classical invariance. That means that gives you a very good hint that this theorem also is true. That we mark. So this f go from h upper star to this does not preserve the classical ring structure cohomological and nevertheless we're trying to say that it preserves the quantum ring structure. We want to say. And so this is really where the so this somehow is counterintuitive, because for mathematicians we used to think Gromov Witten theory as some kind of formal series, and quantum ring is somehow deformation of classical ring. So to identify two Gromov Witten theory, you have to identify it from classical theory and build all the way up. And in this case, the difficulty is you cannot do that. I mean, your classical ring structure, you can actually compute. We compute this explicitly, the discrepancy of the ring structure. So you can actually show how much they are different, and there is an explicit formula to show this. And so then you see exactly because of this sort of you see there are missing constant term. So the constant term, the discrepancy of the classical ring structure, is exactly compensated by when you do this flipping 1 over q. Then that discrepancy constant term exactly compensates that. So that's sort of it's really something which is very interesting. I wish I have a better explanation of how this happens, but this is true. It's that's why this Crepant transformation thing is really intriguing to me, how this can hold. Okay, so that's what I want to say. Okay, now, so maybe for remaining 26 minutes, I will explain how I'm going to prove this case. I mean, I will explain many approaches, and none of the approach actually works straightforward. I mean, so far, I think we might have found a way, sort of a narrow path, sort of going through many approaches and combined together. I'm really hoping all approaches will work, but if you have good idea, let me know. So I'll explain how we're going to work. So the remaining part is going to be slightly more technical. So how can I prove this? I mean, first of all, as I explained, this is a birational geometry. So it's doing surgery. So I want to be able to separate. I just erased. So remember x and x prime. The difference is like in the neighborhood of exceptional loci. So I want to first sort of concentrate my problem in the neighborhood of exceptional loci. That's the first goal. So it would be great if I can say Gromov Witten theory of X somehow it's Gromov Witten theory of X minus Z and plus Gromov Witten theory of neighborhood or sort of tubular neighborhood of Z inside X. If that were true, then I can also write Gromov Witten theory of X prime as Gromov Witten theory of X prime minus Z prime plus Gromov Witten theory of neighborhood of X prime, Z prime to X prime. And since I know they're birational, so these two, the open part identifies. If I can say that, that would be great. So these two are identified, and I only have to study this neighborhood. So this would be sort of a naive idea. In fact, this doesn't hold because Gromov Witten theory is an intrinsically global theory in the sense that you remember the Gromov Witten theory really study modular space of maps to X with fixed curve class. And this fixed curve class is not fixed curve, and the curve class can certainly degenerate in many ways. So even if I start with some kind of curve which lies completely outside of, in the open part, and this curve can easily degenerate. You can find, it can easily degenerate to something like this, for example. And one component will be completely lying inside your exceptional locus. That you can easily find example like this. So that's not good, because then this guy involves study of exceptional locus. So it's very global. I mean, you cannot say, oh, I'm going to do this. Fortunately, there is somehow a sort of approximation of this, which is, has been mentioned, is the degeneration formula. First by Yuan-Pin Li, and it has been mentioned by Yuan-Pin and Yuan-Pin Li, and then later in the algebraic category by Jun Li. That there are also other versions, but this is the version I'm going to use. They're identical. One is in algebraic category, and there are other versions which are not identical, which I don't know how to use. But anyway, so the degeneration formula tells me more or less like this, just a lot more complicated. So now I cannot use Gromov Witten theory. I have used relative Gromov Witten theory, etc., etc. So it's a little bit more complicated than this, but more or less that's the idea. So now, and so it basically says Gromov Witten theory of X can be written as relative Gromov Witten theory, not really on X, but relative Gromov Witten theory on the pair of blowing up of X and then the exceptional divisor. And then somehow, in a certain convoluted way, to relative Gromov invariance of the projective bundle of Z of normal bundle of Z inside X, the projective completion of your neighborhood of this same E. So somehow this way. So, but these parts are the same. So this is the same with the X prime part. So this enables us to deal with only this part. So we're reduced to somehow this local model. And then, of course, these are relative invariants. You have to go through some kind of sophisticated machinery of relative back to absolute. But anyway, so we have to study the Gromov Witten theory on the projective completion. So some kind of completion, projective bundle completion of the tubular neighborhood. Okay. So this bundle or tubular neighborhood embedded into that is completed at infinity. So that Gromov Witten theory is good when you are studying projective. The target has to be projective. So that's what we want to study. And the same with X prime side. prime. So that's what we want to study. Now, so here we have to get very technical now. So how can I study this? I mean, if you look into the literatures, and so most of these are, so first of all, this Crepant resolution, Crepant transformation, mostly you can study. So why I'm interested in studying this, because you see even this local model is not explicit. So the difficulty here is. So here is this Z is a projective bundle over an arbitrary base. So it's non-explicit geometry. It's not homogeneous space. It's not toric. Fiber-wise, it's toric, but it's not toric itself. So it's non-explicit geometry. The third thing. Second thing here is it's not semi-final or semi-positive. And that is really where the difficulty comes from. And you might say, oh, well, of course, non-explicit geometry means it could be non-semi-final. But even if you take explicit geometry with non-semi-final case, it's very difficult. I mean, if you ever try this, it's very difficult to compute. So I'm going to propose a few ways to do this. As I said, none of these, so far, the way I can make it work. I mean, many of these all of these should be able to work. I mean, in principle, all the way through. But I wasn't able to push any approach all the way through. So first of all, let's just say, hey, well, these f and f primes might not be decomposable. So let's assume. So if we assume f really is a direct sum of line bundles and f prime is direct sum of line bundles, then as many of you know, now I have localization in the fiber. So I can do a localization. So these projective space or projective space over projective space. So this is basically, this projective completion will be some kind of double projective bundle over an arbitrary base. So you say, hey, if I know, of course, I'm assuming I know the geometry of base, well, which is arbitrary, but that's sort of part of your data. You want to study this local geometry. You can say, hey, let's localize. Let's localize. So it's going to be double projective bundle over the fiber, and you can localize. So the first approach will be to localize. Well, when you localize, let's just say somehow it's a toric case. So you have your base will be S. Then you have some kind of fixed section in your target will be something like this, and then there will be some kind of and so you will find your fixed sections. Fiber-wise, you have some kind of fixed section. This will probably like that. These three will be your fixed sections. Well, and then each fixed section will be the same as your S, your input data. So that looks pretty good, except that you also need to take care of the sort of this normal bundle in the. So you need to so each fixed section you have to integrate over somehow this neat Gromov Witten theory of this, maybe you say twisted Gromov Witten theory, in the sense of like I need to insert this this virtual normal bundle in the modular space of stable maps, which wasn't explained, and I'm probably not going to explain. But anyway, so you need to do some kind of twisted Gromov Witten variant theory of S. So it's not just S, because you need to, if you know anything about localization, you know you need to take care of I'm doing localization in modular space of stable maps, which have which is virtually smooth, and localized. The fixed locus is also virtually smooth, but So the virtual normal bundle is not going to be, it's going to be added data to that. And so in any case, this twisted can be untwisted by sort of this machinery developed by Giventhal and Giventhal codes. So there is some kind of Riemann rock, etc. So in genus 0, at least, this is done by Jeff Brown, and plus maybe Giventhal, that they prove they have some kind of good formulation. I mean, as you probably heard from Renzo's talk, that doing localization, it's a little bit like algorithmic or mechanic, but the difficulty is really to organize your data in a good way that data actually makes sense. Otherwise, you end up with summation over bad comparators which you cannot deal with. So you need to be able to organize your data in a certain way, and that's when the good generating function will help you. But in any case, this is something which can be done, at least in genus 0. So, and you think, well, let's do that. Okay, now if I can do it. So, but then what happened with this is the following. So the way Brown-Giventhal's result hold is they identify some kind of fiber-wise hypergeometric series. As in Hiroshi's talk, you have fiber-wise hypergeometric series, which is a good data. And what they say here is you have explicit algorithm called Birkhoff factorization to get to the Gromov Witten theory. So anyway, maybe we'll say that what Brown-Giventhal does was to write down what the, I mean, it's really relatively very easy to guess what the I function should be. It's basically, it has to be, yeah. Anyway, so it's very easy to write down what I function is. So this I function of this local model, I'm going to change my notation. I'm going to call my X to be the local model anymore now. So just for easier, this is can be written as some kind of input of some fiber-wise hypergeometric series, and then somehow mixed with, convoluted with a base S J function. And so from here, you can get to the J function by explicit algorithm, which is kind of complicated, but explicit, called Birkhoff factorization. And so, okay, now here is what we got stuck. The I function itself is not, this guy does not analytic continuate. This is actually a bad thing. But when you do Birkhoff factorization, you see that all the poles and everything get canceled turn by turn. I mean, it's sort of a miracle. I mean, you have to do it by hand, and then you see all these complicated poles, log poles, all the poles just get canceled. So okay, so I'm taking this QD. I'm taking about this Q, and QD. So if you want this to be analytic function, you better be here. Okay, so I didn't say it very clearly. So how can I make something analytic continuation? That means, well, I'm going to rewrite this stupid series I just mentioned. I can write this in the following dumb way, or a very interesting way. I mean, look, this is, you can write that series as some kind of, we call it Euler series, which is like this. Is equal to 0. Of course, this is nonsensical. This holds in that sense, right? So if I sum from negative infinity to positive infinity of this becomes 0. This holds in that sense. I mean, this, of course, by itself doesn't make any sense, but it holds in that sense. And so that means there are two things which are analytically the same, right? So means this side and that side are analytically the same. And so I write it like this. And what else could be could be analytically the same. Well, if I take the polynomial differentiation of this, then I'll be the same. So for example, if I take q ddq, some kind of polynomial of this, then this will be something like p of d, qd, and missing some terms, well, equal to 0, right? So this will be a polynomial in D. If that is the case, then I still get analytic continuation. What is not analytic continuation is this P of D has poles in D. Then it stops to make an analytic continuation. So the I function, if once you write down, you see the poles comes out. Then you do Berkhoff factorization term by term, you see the poles just get canceled. And we test this on a simple example. It all work, but it becomes sort of harmonic series in D, then double harmonic series, triple harmonic series. I just wish I'm smarter than I am. So unfortunately, I'm just myself. So I cannot cancel the poles. So that's something which I cannot do. So the approach 1 gets stuck. OK, so I have 10 minutes. I'll get to other approaches. So approach 1 gets stuck in the beginning. But there are sort of bright side of this. In the case, maybe I'll say this later. So this is the first approach we try. Not chronologically, but there is some kind of approach. Try. I say, hey, then you say, well, look, you should get smarter. Like I function is really solution of some kind of system. So fiber-wise, for example, if you know I function, it's a hypergeometric series, right? So it's going to be some kind of Picard-Fuchs system in the fiber. So the second approach would be say, well, you study the differential system or D module associated with I and J function. And that's sort of better because you see the J function itself has descendants which is not analytically continued. I didn't say it. So J function itself does not necessarily, when it has descendants, it no longer works. I explained this in summer school. I'm not going to say too much. So J function itself, only the primary invariants or ancestors are has analytic continuation. Descendants do not. But the function, the J function satisfies quantum differential equation, which certainly, if you believe what I said, they are all constructed from primary invariant quantum product. Therefore, they have to have analytic continuation. So you can study differential system, which is more intrinsic than the solutions. I just start with playing with solution, very complicated solution. I failed. So maybe it will be smarter to study differential systems. The problem with this is, well, you know what the differential system related to J is. It's just quantum differential equation, right? But that's exactly what I tried to find. So I cannot, that's what I'm trying to find. So that's certainly, I have to start with I. But for I cannot lift. For I know, for I don't know how to lift this differential system annihilating I from S to X. X again is a local model. So remember, this is a convoluted way of fiber hypergeometric series, which is toric variety with base, which is S. And suppose I know S. This is the input data. So I know differential system on S. It's J function S, which is quantum differential equation for S. I know how to write it down. Well, so I want to lift this to a system in X. I know what fiber direction is going to be. Fiber direction is somehow modified toric data, so I can write it down. But for horizontal, I don't know how to lift that. So this gets stuck again. Unfortunately, this gets stuck also. And so the third approach will be use this. Well, okay, so apparently this is a very difficult problem, at least for myself. I never worked on a problem which is really equal in difficulty of this problem. Never. So this problem is really difficult for me. So anyway, so the third approach, so I mean, look, I tried 2 approaches, want her to try a third. A third one is to say, hey, so S is arbitrary. Where does that sort of difficulty comes in? Now, suppose I can deform S in a certain way, so you will make it work. For example, we know Gromov Witten theory is deformation invariant, right? So why don't we deform S? Of course, if you just deform S, it won't nothing is going to happen too much. What if I can degenerate X? So I'm going to deform. In fact, I'm going to do double point degeneration. Of S. In fact, I cannot just degenerate S. Remember, locally, my local data is going to be looking like 2 vector bundles over S. So now I have this data. I have this data which is bundle or list of 2 bundles over base. So I want to see how I can do this by double point degeneration. How I can deal with this. And this is what why I work on this algebraic cobordism. So you can study. And the degeneration formula hold. So the reason to work on this is so now let's try this something called algebraic cobordism. Which means that you have list of vector bundles and then a smooth projective variety. And you can say, hey, I'm going to deform this so that in a family, so that these bundles be summation of this such that this Fi will all be direct sum of Li line bundles. Direct sum of line bundles, and in fact, they will all be base point free or generated by global sections. All the F for Oi, and the S will be some kind of toric, for example, projective space, product projective spaces. If I can do that, and I know under double point degeneration, I have this again, this degeneration formula, which, as you know, been recently generalized to sort of 3 point more general normal crossing divisors. But here I'm this old version. I mean, that probably you will hear from others, or you can ask maybe people in the Abramovich group who can explain this. I don't know about that, but at least for double point degeneration, I do have degeneration formula. So I'm hoping that, well, maybe I can recover this from these data. So if I can degenerate into this case, then I just prove this case, and I track it back. I'll get what I want. Well, unfortunately, it still doesn't work for me. So that's sort of why it doesn't work. It was the following. So degeneration formula is really. Oops, I only have 1 minute. So degeneration formula is something like this. As you know, the Gromov Witten invariance for X, it can be written as relative Gromov Witten invariance. Relative or absolute, it really doesn't really matter. So X tilde or Y relative some kind of, maybe I'll say Y, is blow up, and then convolute it with relative Gromov Witten invariance of this projective bundle. And so this is, so if you're going from, if you know both these two, then you certainly know that, no problem. The problem is, because this algebraic cobordism is defined in a certain way, such that it's not always sort of forward degeneration. Sometimes you know these two, you want to know that. And so you have to prove this this system give you some kind of, somehow it's invertible. Given these two, then I will have to be able to know this. And that part, I don't know. Unless you can find a specific path in this algebraic cobordism, this double point degeneration, from what I want to that, which always either forward degeneration, or when you go backward, I can only prove if I know these two, and if this Y is if this is deformation to normal cone, then this system is not degenerate. So knowing this two would automatically imply the middle one, only for deformation to normal cone. And for general double point degeneration, I cannot say that. So that's the problem. So otherwise, this will be good. So after these three tries, it's still not. I mean, so we're still cleaning up the data. But I think one possibility is to take the first approach and prove it for base point free case. Then to use this to reduce base point free case. This is you can easily reduce to base point free by blowing up, blowing down, and deformation. So that's sort of narrow path I'm talking about. But all these three should all work. I'm just not able to make it work. Okay, thank you. Yeah. So I mean, I don't know a lot about that. So my guide of this derived category, I mean, is that well, I mean, so first of all, derived category itself is sort of more topological and linear object. It's more localized, and sheaf we can talk locally. Gromov Witten talk about curve class always move around. So, but if you have derived equivalence, you certainly have K equivalent. You have a K group equivalence. Then you certainly have some kind of cohomology equivalence. So that will help me with the first step to identify them classically. And to get the second step from derived things, I think you probably need to go through this Bridger stability. Probably try to find this Frobenius manifold from this stability manifold, some kind of construction. We've seen some kind of very simple examples, for example, from Emmanuel and Aaron's work. We know there's some kind of simple example. They were able to construct this level 3 elliptic curves Frobenius system from the stability manifold. But it's all very local and primitive at that stage. So I don't know. I mean, that